Hi, everyone. We are very excited this week to have David Marsh here to tell us about Axions. He is absolutely one of the leading experts in modern Axion research, so it's a great pleasure to have him, and I'm very much looking forward to what he's going to tell us. So take it away, David, when you're ready.
Thanks very much. Thanks for the invitation. And it's a pleasure to be here. And yeah, I'll get started straight away. So I'm going to tell you today about the post-inflation QCD Axion, and hopefully it will become apparent what I mean by that as we get on. But before we start talking about axions, I've got to tell you a few other things. So I'm going to be talking about axions as dark matter. So dark matter, it's out there, it's in the cosmos. And what do we know about it? Well, from the cosmic microwave background anisotropies, as measured, for example, by the Planck satellite, we know very well the cosmic dark matter density. So what you do is, of course, you measure, for example, the 2-point function of the temperature of the CMB, but also the polarization, the lensing, etc. And that is given by the data points here, and then you fit a 6-parameter theory to that called lambda CDM, and one of the parameters that you derive is the dark matter density. And this is all really well understood linear physics and very, very precise. And from that, we learn that the dark matter density is approximately 4 times the density of the baryons, the ordinary matter. We express this as this quantity here, omega d h squared. It's just a dimensionless measure of the energy density. And it's about 0.12, and it's known to about 1% precision. This is one of the numbers I'm going to be using later on to constrain axion theories. The other thing we know about dark matter is it's here on Earth, or at least at the solar radius in the Milky Way. And we know that from different measurements, and they involve also fitting theories, but there's a lot more uncertainty because the Milky Way is a messy place and the CMB is nice and linear. So this is a measurement of the Milky Way rotation curve as a function of radius, the circular velocity in kilometers per second. We're here at the solar radius, something like 8 kiloparsecs from the galactic center. And if you fit the models here, they're shown as the bulge, the center of the Milky Way, the disk, the stars that we live in, and then the dark matter halo. And you see that the stellar radius, dark matter is, about an order 1 fraction contributing to the circular velocity, and it becomes increasingly more dominant further out. This is what gives us flat rotation curves. And from measurements like this, we know that the dark matter density on Earth is about 0.3 GeV per centimeter cubed. There's a lot of uncertainties associated to that, but you only need to know the scale of it, really. If you want to know what 0.3 GeV per centimeter cubed is, well, it's about a solar mass per cubic parsec, but it's also, of course, about a proton in a centimeter cubed. And to give you a human feel for that, or a squirrel feel for that, if you took all the atoms in the body of a squirrel and smushed them up and spread them out throughout the entire volume of the Earth, that's about the density that we're talking about, 0.3 GeV per centimeter cubed. Enough about the evidence for dark matter. I want to tell you why axions are an interesting thing, why you might think that the QCD axion exists. And this goes back to something called the strong CP problem. This has been known for a long time, since the 70s. I'm showing you the latest measurement of it, latest expression of it, which is the measurement of the neutron electric dipole moment. I'm showing you here 2 young PhD students who I worked with in 2017, actually using these measurements to try and search for axions. This is Mikhail Rolik and Nick Ayres at the NEDM experiment in Switzerland. They're stood in front of the experiment. What you can see here is a bottle, essentially, and this bottle has cold neutrons pumped into it. Then they're hit with electric and magnetic fields, and if they have a dipole moment, it separates the population. It's something called Ramsey interferometry. And they don't measure a neutron electric dipole moment. They measure that the neutron electric dipole moment is 0 with a precision of about 1.3 times 10 to the minus 26 e centimeters. It's an electric dipole moment, so it has units electric charge times distance, e centimeters. A dipole moment, and you have to think about this, and there's a good cartoon of it on Wikipedia actually, violates charge parity symmetry. So if you make a charge flip, you will reverse the electric field, and if you make a parity flip, you reverse the magnetic field. It's because they're vectors and pseudo-vectors. This violates CP symmetry of the strong nuclear force. Neutrons made of strong nuclear force stuff. This is expressed at a fundamental level by something called the QCD topological term. So here's the Lagrangian, and part of the Lagrangian of the standard model. And the terms here are trace GG dual. G is the gluon field strength tensor. The trace is over the SU3 space, and the dual has its indices raised with the epsilon tensor. That's what makes this CP violating. And this coefficient, this dimensionless coefficient here, theta. Now, I don't have the citation here. This was worked out in the 70s, how you can work out the neutron electric dipole moment induced by this theta. They both have the same symmetry, so it's kind of obvious they should be related. And the neutron electric dipole moment should be 3.6 times 10 to the minus 16 e centimeters times theta. So, okay, theta's close to 0. Big deal. The reason this is a real fine-tuning problem for the standard model is that theta also has a contribution from electroweak CP violation. So we know that the electroweak interactions violate CP. For example, K-on decays, the CKM matrix, Nobel Prize for K and M. And the actual measured theta is the theta that you would have from writing down QCD plus something related to the complex part of the quark mass matrix. So you can make chiral rotations of quarks and make the quark mass matrix purely real, but this comes back to haunt you and reappears through the determinant of the quark of the quark measure in the path integral. Comes back and gives you a theta on the GG dual term. So one part that we know is non-zero, CP violation in the electroweak force, and then something else from QCD have to cancel at dimensionless level of 10 to the minus 10. But there's no symmetry of the standard model that says this should be 0. The standard model violates CP. But the strong sector of the standard model seems to conserve CP. So this is a mystery. Enter the Axion. So in 1977, Peccei and Quinn, and then shortly later Weinberg and Wilczek pointed out that there was a particle, had the idea that you can solve this problem if you make theta dynamical and then give it a potential where the potential is minimized at the CP conserving value. So theta, if theta can evolve, you will dynamically solve the problem. So this is the recipe for how you do that. You start by introducing a symmetry, a theory with a global U1 symmetry, a global complex rotations symmetry. And you do this with a field called the Peccei-Quinn field, after Peccei and Quinn. So the Peccei-Quinn field is this complex field phi, and it has a classic wine bottle potential. So you have spontaneous symmetry breaking, and you have a Goldstone boson. So if you write the field around its vacuum, it has some vacuum expectation value V, that's given by the radius of the wine bottle, and then it has a Goldstone degree of freedom theta that runs around the bottom. Okay, haven't solved the strong CP problem yet. Next, you have to do something. You have to chirally charge quarks under this U1. What that means is that the quarks pick up a different rotation, whether they're left-handed or right-handed. If you're writing this as Dirac quarks, then you just write this rotation by this U1 as U1, e to the I gamma 5 theta. So it's a rotation that cares about which part of the Dirac spin you're in. This is where the magic starts to happen. Chiral symmetries are anomalous. What that means is if I take this diagram where the dotted line is the theta Goldstone boson, it interacts with the quarks, then I can draw a loop and the quarks can emit 2 gluons. And for a normal U1 symmetry, for a vector symmetry, this has to vanish. But for a chiral symmetry where I've got a gamma 5 on this vertex, this diagram doesn't vanish, and it's equivalent to an interaction term in the Lagrangian theta GG dual. So you see where the epsilon comes from. Okay, imagine taking a trace around this loop using normal Feynman rules. You've got gamma mu's from the from the quark propagators, and you've got a gamma 5 on the vertex. And when you take traces of things with gamma 5, you get epsilons. So that's where you get the GG joule. Now you've got your whatever your original theta was, theta QCD plus the quark plus the argdet quark mass matrix plus this field theta. I can absorb the constant into theta, and that just corresponds to some different place around the bottom of the wine bottle. So now I've just got a field. I've got rid of my problematic number, I've just got a field. This is where the second bit of magic happens in the theory, something called instantons. So these are field configurations in QCD where the SU3 field wraps spatial infinity, and they carry energy. They're the theta vacua of QCD. And a calculation that you can see in the lovely symmetry book by Coleman, in what's called the dilute instanton gas approximation, you see that the vacuum energy goes like minus cosine of theta, where theta is the coefficient of GG joule. So therefore, you can write that as an effective potential for theta. The vacuum energy depends on theta, write it as an effective potential in the effective action. This has the effect, if you think what's cosine theta, it's just something linear tilting the potential along the real axis. It has the effect of tilting the wine bottle and thus giving an effective potential to theta. This theta Goldstone degree of freedom is now the Axion. It moves down the potential to its preferred value at 0. The reason it's 0 is due to something called the Vafa-Witten theorem. And it cleans up our CP problem. So we had this problematic number. Now we coupled it to a field. We gave the field a potential. Field minimizes potential, problem gone. The Axion has cleaned up the CP problem. And that's why Frank Wilczek gave it that name. So there we go. The Axion, our top CP cleaner. But it gets better. Dark matter. I'm here because I'm a cosmologist and I'm interested in dark matter. And the Axion solves that problem for you too. So this new pseudo Goldstone boson, it's got a mass. It's got a mass set by the scale of the quark masses in QCD, and it's this number here. The constant F I'll be talking about quite often. This is called the Axion decay constant. It's related to the VEV of the Petché-Quinn field by something called the color anomaly. I can go into that in the questions, and I'll mention it once more later. Don't have time to explain it now. The Axion is a pseudo Goldstone boson. You can set up oscillations in this field, exactly the mechanism that solves the strong CP problem. The relic oscillations in this field happen to behave like dark matter. This is called the realignment mechanism, and I'll go into it a little bit more in a few slides' time. What I want you to know now, at this stage of the talk, is that you've got this oscillating field, this field oscillating about its potential minimum, and it has an angular frequency omega, given by the mass plus a half mv squared plus, higher order relativistic corrections. Dark matter is non-relativistic, so we can easily stop P at half mv squared. That means the frequency is basically the mass plus or minus 10 to the minus 6. If you remember from my plot of the circular velocity in the Milky Way, circular velocity is about 100 kilometers per second, so the frequency is very well just the Axion mass, cold non-relativistic particles, right? So the scale of the masses is small for allowed values of this decay constant. Again, I'll come back to this. 10 to the minus 6 EV means that the frequency that this field oscillates at, just restore the factors of H bar and C, is 1 gigahertz. Okay, so radio frequency oscillating field. The local dark matter density in this case is just a harmonic oscillator. It's a half m squared phi squared, where phi is the amplitude that the field's oscillating at, and it's related to the theta parameter by this constant Fa. So there's just one parameter. There's one parameter in the model in principle. It's just this constant Fa, which determines the particle mass, and it also happens to determine all of its interactions. So you've got a one parameter dark matter model that's very attractive. And what is Axion dark matter? Well, so okay. Hello.
Sorry.
I wanted to
I wanted to paint a picture.
Hello?
Sorry, I'm having crosstalk, which is why. David, can you just state again the upper and lower bounds on the mass in the model? Or the actual mass?
Haven't got there yet.
Okay, good.
That's the next slide. So I'll come to, I've picked this mass, it's about in the middle of where you can be, and I'll give you the bounds on the next slide. So axion dark matter, every field's a particle, but what's this field? The dark matter in this case, it's really spatial and temporal variations in the neutron EDM theta parameter, plus potential energy carried in QCD instantons. When you think of it like that, it's actually kind of strange type of dark matter. But of course, there's particle excitations of this field, and you could also just think of it as a load of cold particles. So now the Axion is an even proved theory. It now also has dark matter as well as solving the strong CP problem. But the question just came, which is, what is the Axion mass? So I'm going to tell you the rough range it lies in, and then hopefully we're going to zero in on a particular range of that in a particular cosmology. So first of all, for the QCD Axion, we know that its mass has to be less than about 10 to the minus 2 electron volts. And that's because the couplings of the Axion all scale like 1 over the decay constant. So they're all proportional to the mass. So more massive Axions are more strongly coupled. And this particular bound comes from the Axion coupling to nucleons. So because it has this coupling to gluons, it also has to couple to nucleons. It couples to protons and neutrons. And if the Axion did couple in that way, it would be produced inside supernovae and escape from them and cause them to cool. And the particular constraint comes from supernova 1987A. If Axions were produced too much, the supernova would cool too quickly before it could release its neutrinos. And we wouldn't have seen a neutrino burst at the same time as supernova 1987A. But we did. I think there were like 5 neutrinos detected concurrent with it happening in 1987. So we know that Axions can't be too strongly coupled, or they would spoil this amazing observation, really, that you saw a supernova in both photons and neutrinos at the same time. And this tells us the Axion has to be light, and the exact number is about 10 to the minus 2 eV. We also know it has to be heavier than a certain value, and I'll zero in on this as we go. We know it has to be heavier than about 10 to the minus 22 electron volts. That comes from bounds from what's called fuzzy dark matter, basically something that I've worked on quite a lot, but it's not what this talk is about. If the Axion is too light, then its de Broglie wavelength is bigger than a galaxy. And if it's bigger than a galaxy, then it can't cluster inside galaxies, and so it can't really be the dark matter. That's essentially where the bound comes from. So that's the absolute lower limit on the mass. But I told you the Axion mass is inversely proportional to this decay constant F, which is the vacuum expectation value of a field. Now, we'd be concerned if a vacuum expectation value of a field is larger than the Planck scale. Energy scales larger than the Planck scale are generally not things we like in field theory. So that says that Axions lighter than something like 10 to the minus 12 electron volts can't really be the QCD Axion in a sub-Planckian theory. So these very light theories of dark matter, fuzzy dark matter, are exotic. You can get them from Axion-like particles in string theory, but it's not going to be the QCD Axion or the normal QCD Axion. There's one more bound that gives us a good bracket for the QCD Axion that's a bit better than just the F can't be bigger than the Planck scale. And that comes from black hole superradiance. So if Axions are in a mass range between about 10 to the minus 11 and 10 to the minus 12 electron volts, bracketing that Planckian scale and a little bit larger masses, they would be resonant with the sizes of spinning astrophysical black holes. So black holes of 1, 10, 30 solar masses are observed, and we know their spins. We know their spins from, say, the in-spiral phase fitted from LIGO, but also from observations of the X-ray accretion disks. And we know that there exist solar mass-ish black holes that are spinning. If the Axion Compton wavelength is resonant with these black holes, it would form a cloud around them, that extracts the spin. There's an instability to the effective Schrodinger equation on the Kerr spinning black hole background. This excludes a range of masses between about 10 to the minus 11 and this more fuzzy end of Planckian axions. And that's very nice. That tells us that the QCD axion has to live here. 10 to the minus 11 to 10 to the minus 2 EV. Now that's a big range. That's 9 orders of magnitude. I'm going to try and make that a lot smaller by carefully choosing my cosmology.
Sorry, so the super radiant bounds you're talking about, do they care that it's a black hole axion? I mean, a QCD axion versus any other axion? Okay.
They just apply for, they in fact apply for any massive bosons. You can get bounds on massive vectors, massive spin 2 particles, as long as the self-interactions aren't too large. For the QCD axion with the Fs of relevance here, it turns out the self-interactions are actually small enough. So it assumes small self-interactions, and it applies for any massive boson with like slight changes based on the spin. My colleague who I worked on this with, Matt Stott, wrote a paper recently giving the bounds for spin 0, spin 1, spin 2 recently. So the next thing in this kind of introductory half of my talk, where I kind of want to motivate you to be excited about what I'll tell you later about axions, is I want to compare axion dark matter to WIMPs. These are 2 historical dark matter theories proposed in the 70s and 80s. Okay, what's the like rough experimental situation? So let's look at WIMPs. So here's the way you normally think of WIMP dark matter searches: cross section versus mass. The theory, and this is some particular scan of the CMSSM, lives in this region here, narrow region, predictive model. You know what the cross section is and the mass is if you're going to be all the dark matter, but the experiments are very good, and all the regions above the blue lines, these are I think from Xenon and CMS and CDMS. The regions above the lines are excluded. So a lot of the good parameter space for WIMPs is already probed. There's of course an important region here where we should still be looking, the neutrino floor still to reach, but the experiments have been very good at probing the theoretically predicted parameter space. In axions, we're in a much poorer situation. The theory is the QCD axion. It predicts that there's a relationship between the mass and the coupling of the axions that's linear. But it doesn't tell you where you are on that line, and the line's got some width. But the experiments have really have probed this. This is ADMX that I'll talk about later, but there's a lot of parameter space wide open at the moment. Now this story of the axion is the thing that has got everyone excited about axions in the last decade or so, that there are now lots and lots of ideas, and I'll talk about some of them towards the end of the talk, to change this situation. And axions, you know, in the next decade or so should be in a situation much more like WIMPs are today, where we've excluded lots of the exciting parameter space, and we could be in a situation to say whether the theory is ruled in or out by experiment. But at the moment, the experiments are only able to probe narrow parts of the parameter space. So that's about the end of the motivation part of my talk. Now I need to tell you why this post-inflation axion is interesting. So axion cosmology. The key thing is where the spontaneous symmetry breaking happens in the cosmological timeline. So 2 possibilities that separate into 2 classes. If the spontaneous symmetry breaking happens before or during inflation, then inflation blows up the axion field to have just a single value across all of the observable universe. Great, nice, simple theory to solve. It obeys the Klein-Gordon equation, and the Hubble term plays the role of a friction. So what happens is the field starts at some value, but starts at some random value, and then evolves and oscillates. And it oscillates when the friction term becomes small in this equation. And the relic density is, as I said, held in the oscillations of this field. But you can't predict the axion mass by only telling me what the relic density is. Tell me the relic density is 0.12. This doesn't tell you the axion mass because there's an additional continuous free parameter, in this case, theta I. So in this case, basically, the axion could be anywhere in that 10 to the minus 11 to 10 to the minus 2 EV range. But there's another possibility for the cosmology. If the spontaneous symmetry breaking happens after inflation, this leads to our patch of the universe at the bottom here having many different patches of this angle, of this axion angle theta. Now that might sound worse, but well, it is worse computationally because the Kibble mechanism means that this patches of thetas actually correspond to topological defects in the Peccei-Quinn field. You still get dark matter because these defects decay when the axion mass switches on and produce the oscillations in the axion field that we need for dark matter. The reason that this is a nice scenario is that continuous random number that we could pick in the other scenario kind of gets averaged out here and leaves us with just the one parameter again, the axion mass. So in principle, this scenario is predictive. If you tell me the dark matter density in this scenario, I should be able to tell you the axion mass. But it's not that simple. Unfortunately, the dynamics is complicated. To solve the decay of these defects, you have a nonlinear partial differential equation, and you have to solve it using classical lattice field theory. Okay, I mean, people can do that. What's the problem? The problem's illustrated very nicely in this figure from Marco Gorgetto's paper from a few years ago. So the topological defects that we're interested in here are cosmic strings made of the winding of the axion field. And the strings form at spontaneous symmetry breaking. And that happens when the Hubble scale is around the axion decay constant scale, the Peccei-Quinn scale, of, let's say, 10 to the 10 GeV. But the strings only decay when the axion mass becomes of order Hubble. And as the universe expands until that happens, and so relative to the size of the universe, the strings shrink and shrink and shrink and shrink. And now you have to resolve scales when Hubble has gone to the axion mass scale. And now computationally, you can only really resolve the logs of these scales down to a log of about 6. So a numerical problem means that you can't solve the problem that you want to solve for the physical value of the separation of scales. And the physical scale is log of 70. So e to the 70 separating the Peccei-Quinn scale, 10 to the 10 GeV, and the axion mass scale of a few micro EV or milli EV. So computational problem means you can't solve this problem exactly, and there's a large theoretical error. So now I've told you lots of stuff that is known in the literature, and I'm halfway through my talk. And through the next half, I will tell you 3 things that I've been working on recently in this scenario. For the next 2 sections, I'm going to be assuming something. I'm going to be assuming that this n I introduced before, the color anomaly, is equal to 1. If you want to know about the case when n is not equal to 1, or what n is, if you don't know what n is, please save any questions about that until the end, and I'll be happy to talk about it for a while. So the first of the 3 things I want to tell you about in this post-inflation axion scenario that is in principle predictive is, can we predict the axion mass from the relic density? And this is based on work that I've been working on with a master's student, Jana Ries, and Seb Hoof at Gottingen. And this is something we hope to be putting on the archive in the next month or so. And what we're doing is we're trying to do a statistical treatment of the best available simulations of this topological defect decay. And we want to use it to predict the axion mass from the requirement that the dark matter density is its observed value. And we want to do this in a statistically rigorous way, so we can say this is what we think the mass is with a given error, and including errors like the QCD errors, for example, from the quark masses and the topological susceptibility and things like that. So this is the cartoon of what our pipeline does in terms of cosmic time. We include the possibility to produce hot dark matter. So the axion is made as a hot component by its interaction with pions. You have this realignment contribution, the kind of average oscillations of the field, for which we've written our own module, including the QCD uncertainties. And then we compare fits from what we consider as some of the best available simulations for this. There's some by the Japanese group and by the Italians, Marco Gorgetto. And each one of them simulates different things. We're interested in strings being produced during the scaling regime, decay of domain walls, for example, and this era called the nonlinear transit. After the strings have decayed and when the axion field eventually enters into a linear regime. And then at the end of this linear regime, you just have, at the start of this linear regime, you then just have free oscillations of the axion field, and you redshift them to today, and that gives you your dark matter abundance. So we have to have implementations of all of these things. And we want to have a control over the statistical errors. So what we do is we fit the available simulation results, and within the parameters of the fits that we use, we construct a covariance matrix, and then we marginalize these as nuisance parameters. So here's two examples of how we do that. One is we take the emission spectrum, the instantaneous emission spectrum of axions in the simulations from, in this case, this is from the Gorgetto paper, and following the method that they proposed to do this, and we're implementing it in a statistical way. And so we fit this spectrum. And the thing to know about this spectrum is that it's what's called infrared dominated. If you know about this, it has Q greater than 1. It's an IR dominated spectrum. The next thing that we fit is the string density parameter. And Gorgetto and co pointed out that the string density parameter has what's called a scaling violation. It isn't constant, but it appears to evolve as this log of the scales increases. And if you extrapolate this to the physical log and in a statistically well-controlled way with errors and nuisance parameters, you can get a value for this scaling, for this string density parameter at log of 70, and it's fairly large, right? It's something like 15. These two things combine the IR spectrum, so dominated by low wave numbers, and large string density parameter, mean that you've got a lot of axions produced by the string decay in these simulations. We then fit this model to add up all the different dark matter contributions. And this gives us a lower bound on the axion mass. If the axion mass was too low, then you produce too many axions from the string decay. It goes inversely with the axion mass, because it's proportional to the decay constant, the scale of the energy. And the mass is inversely proportional to that. And then by including also this hot component of axions produced by the interaction with pions, that gives an upper bound on the mass, because that coupling is stronger when the mass is larger, when the decay constant is smaller. So we're able to get a bound for both ends from the axion mass. And we fit this to the Planck data. We don't fit it to the exact Planck data because we're only using standard cosmological parameters. So we don't need to run Markov chain Monte Carlos for the CMB spectrum. We just take the two relevant parameters, the dark matter density and the number of effective relativistic degrees of freedom, and treat the Planck posteriors as a likelihood. Okay, and this is, as I said, the cold dark matter density parameter, 0.12 with an error of 1%. When you do all of that, and we demand that the axion is all the dark matter, we arrive at this result for the axion mass. It's slightly different. So we've used Gorgetto's data, but we fitted it and allowed for other uncertainties, for example, the QCD uncertainties, and we get and we've treated it statistically, and we get a best fit value for the axion mass from our fitting method on their data, on their simulation results. And it's around a milli EV, the best fit value in this case. And that's in contrast to other results in the literature from earlier, for example, the result by Clare and Moore and some other groups that have a UV dominated spectrum instead of an IR one. When you have a UV dominated spectrum, you have fewer axions from strings, and therefore you end up with a lower value of the axion mass to get the right dark matter density. And this is a big question at the moment in the community studying this, is that spectrum UV dominated or IR dominated? We fitted the results of a group that we think are very good simulations. Their simulations are IR dominated, so I get a high axion mass because I fitted an IR dominated spectrum. So it's a big question, is this correct? Is the spectrum really IR dominated at the physical log?
So should the mass be between these two values, or?
If the spectrum is IR dominated, the mass should be 1 milli EV. If the spectrum is UV dominated, it should be 25 micro EV.
But maybe it's not, and it's in between these possibilities. So should the mass in that case be in between these two masses, or how should I think about this? About the uncertainty on the mass.
Well, so from Gorgetto's simulations, the uncertainty on the mass is 0.04 milli EV. Now, what's the systematic uncertainty between the two simulations? You have to decide who you think's done the
I mean, you mentioned infrared dominance or ultraviolet dominance.
Mm-hmm.
Is these two distinct possibilities, and there is nothing in between these two?
No, so there's a continuous parameter. There's a parameter that fits the slope, and we fit the parameter and have an error for it and propagate that error. So the error on the slope from the simulations that we fitted is included in this error at 0.04. Different groups who have IR versus UV, that knocks onto the prediction. But as soon as you become, so in the UV, there's a lot of dependence on what the slope is on the resulting axion mass. So in the UV models, you could be anywhere in between. But once you become IR dominated, the production kind of saturates. I have another slide on that I could maybe show at the end. So in the UV case, there is a lot of uncertainty based on the fitting of the spectrum. But once you become IR dominated, the uncertainty kind of saturates.
Okay, very good. Thank you.
All right. So, does this depend on when the phase transition happens, or as long as it happens after inflation? This is pretty much.
As long as it happens after inflation. One of the other chains that we're running in this study at the moment is to include uncertainty on the relationship between the parameter that controls the axion mass, the Petric wind scale, and the mass of the Petric wind radial mode. So that would be when this, as long as that would be after inflation, but when does it happen after inflation is that uncertainty. We haven't finished those that part of the study yet, though.
Because so maybe I'm missing something. Maybe I'm missing the UV and versus IR dominated. This is sensitive to when the axion was produced dominantly. Was it in the later stage, or what is the reason that something will be UV dominated, something will be IR dominated?
Right. So it has to do with the decay of the strings.
I saw the bulk of the axion, you're just producing them, at the collapse of the axion domain wall, right? So this is I guess that's what you call decaying of the string, I guess. Right? Yeah.
So that's right. So I think that would be the IR dominated case. You produce most of the axions like at the end when the network decays. If you're UV dominated, you produce lots of them early on.
I don't know what's the scenario for, you produce lots of them early on, right? Because I thought that the usual story is you produce the most of them just, at the collapse of the axion domain.
So that is something that the different simulation groups don't agree upon.
So because if it's UV dominated, I would think that it will be sensitive to when the phase transition happens as well. No?
Sensitive,
maybe it's not that UV.
It's not that UV. Because you've got a big separation of scales here. It's UV, but it's not so UV that you're dominating.
Because of course, if you stick to the QCD axions, the mass is not entirely independent of when the phase transition is happening.
Right, exactly. That's the point. So, but you've got this log of 70 scale separation, and if you change the mass, that log goes between 60 and 70. Remember, we had about 9 orders of magnitude to play with in the mass. So you've got a log of 60 or 70, but you're always a big separation from when the phase transition happens to when the decay happens. But you're right that does change the distance between the two. So
then physically, what determines UV versus IR dominance? Is it basically nature of the Pacheco phase transition that determines which one actually happens?
So it's the nature of the strings themselves. So the way that the strings are simulated here is you actually simulate the complex Pacheco field, and the dynamics of that sets up oscillations in the Axiom field. And the thing that's being noticed here is that the spectrum is evolving and the number of strings, and the emission is changing as you change the scale separation. And in their simulations, what Gorgetto and co notice is that as you move from low logs to high logs towards the physical separation, as the decay of the network moves further and further from the phase transition, the spectrum becomes more and more IR. That's what's happening here as the logs change. And also you get more and more strings per co-moving horizon, violation of scaling. So whereas before people kind of did simulations at low logs, and at low logs the spectrum is UV dominated, and then people assumed that the spectrum would remain UV dominated, and then just redshifted everything. And they also assumed that at low logs the scaling density parameter is low, and this logarithmic scaling violation wasn't noticed. So really the thing that causes it, according to Gorgetto and co, is the separation of the scales.
I see, but then one of the things I'm still feel a little bit unclear is that after Pacheco phase transition, I guess you're going to produce Axion as well as this network of a topological defect.
And you keep on producing them until the defects decay.
I see. Okay.
For a continuous amount of time, as long as the defects are there, you keep on producing them, and it's because they enter into this kind of attractor scaling solution. You have to have a fixed number of strings per horizon. And in order to keep the number of strings balanced as with the expansion, you have to emit axions. And that's why you have to use this emission spectrum.
I see. Thank you.
Okay. I'm gonna move on because I've got 2 other quite long things to tell you in now 15 minutes. Okay, so prediction for the axion mass from string decay. But what can we do? Okay, I've told you the axion mass. 2 things in this scenario that are now relevant for trying to find the axion. One is the structure formation implied from the string initial conditions, and the other one is how do we search for axions on Earth with these relatively high in axion terms masses. So structure formation, and this is a phenomenon known as axion miniclusters. Basically, the decay of this string network leaves very large density variations in the axion field. If you're near a string, you've got a big load of axions. If you're far away from strings, you've got fewer. Basically, big density variations on the scale of the string network. And for this case, we use a set of simulations done by Vaquero, Redondo, and Stadler. And this is a snapshot through their simulations, and you can see these large density variations. There's a logarithmic color scale between the low density and the high density patches, and work out like the approximate mass scale of these patches. And these seeds are what we call mini clusters, approximate mass scale of these patches. And the mass scale is about 10 to the minus 13 solar masses, scaling with the mass in this way. But these simulations don't have gravity. So you can kind of get the rough scale, but you can't say, oh, is this what you're going to find later after all of structure formation has happened? I'm going to skip this slide. Ask me about Axion stars at the end if you're interested. So mini clusters, these seeds gravitationally collapse, and the way that we describe this, so this is work done by my PhD student David Ellis. We use the excursion set, and what this is you basically take a spherical collapse barrier crossing problem, the classic what's called Press-Schechter problem, and solve it in real space on your density field, and ask when these peaks cross some particular threshold for collapse. This is a method that was developed by Dick Bond and collaborators from the 90s. The difference with applying this to mini clusters is the threshold for collapse is not a constant like it is in ordinary in the matter-dominated epoch. These are dense structures. They collapse during the radiation-dominated epoch, and the threshold for collapse is large. So we have to use this moving threshold. And to give you a visual depiction of what happens there is here's a small patch of Ficcaro's simulations, and here's these very dense patches. And at here a redshift of 10 to the 5, these patches pass our threshold. So that would be something like 20 or so density threshold. So that means at redshift 10 to the 5, you're forming objects. And as you go on, the threshold gets lower and you start to expand the circles. And so you find that you've then got objects merging. So it's a way of predicting the structure formation. And it works. And it matches the results of n-body simulations, particularly in the pre-matter radiation equality era. So what happens during the radiation era is these rare fluctuations collapse. And so the mass function, which is the number density of objects per cubic parsec in mass bins, grows and expands. And here you see already at a redshift of, say, 6,000 or so, matter radiation equality is about 3,000. You've got objects of about 10 to the minus 11 solar masses, and you've got quite a lot of them. The story changes after matter radiation equality. After matter radiation equality, these objects start to merge and hierarchical structure formation takes over. Then you make what we call mini cluster halos out of these original seeds. And then the mass function starts to evolve differently. The low mass objects start to disappear and you form high mass objects from hierarchical structure formation. And our method matches very well the results of the simulations. And the fraction of dark matter bound up in these mini clusters is about 75%. And some of them are as heavy as 10 to the minus 11, 10 to the minus 9 solar masses. Why does this matter? Okay, so you have to ask what the density profiles of these objects are. And I'm going to separate them into two classes. The hierarchical structure formation after matter radiation equality leads to Navarro-Frank-White like things like you get an ordinary CDM. So this is seen in simulation, and using our peak patch method, we can predict will accurately match the shape of this concentration mass curve that describes the radius of these NFW objects. And we can extrapolate it then, because we fit it, our analytic model can then tell us what should happen at redshift 0, and we can tell you what concentration they should have at redshift 0. Very high concentration, 10 to the 5, but they're NFW, and these are quite fluffy objects, actually. There are also, at this period before matter radiation equality, we have the self-similar collapse, and you have denser mini-cluster seeds. So the early stuff could be morphologically distinct to the later NFW stuff. And it could have not an NFW profile, but a steeper, more power law-like profile. And I'll explain why that's relevant in a couple of slides' time. To try and find these objects, these have not been studied. And this is something that we're looking into. So we can identify in this statistical method that we have candidate objects of relatively high mass, 10 to the minus 10, 10 to the minus 12 solar masses, and these large overdensity parameters present at matter radiation equality, these rare dense things. And the question is, do they survive as the substructure in the halos in the n-body simulations? And we want to try and trace these objects that haven't been studied before, not the mini cluster halos, but these dense seeds, and see whether they're really there and whether they're morphologically distinct to the NFW class. That is because the power law halos and the NFW halos behave very differently. So I have to say this quite quickly. So if 75% of the dark matter is locked up in these mini clusters, direct detection of mini clusters is over. You can't detect the QCD Axion, they'll never collide with the Earth. The collision rate is too low. Fortunately, if they're NFW, due to tidal stripping, about 50% of them will be tidally stripped at the solar radius. So you'll still have 50% of the dark matter to try and search for. So that's great. But if there's a lot of power law profiles, they're denser, they're not so easily tidally stripped, and about 100% of those survive at the solar radius. So it's a really important question to ask how much of this dark matter in mini clusters is in early power law types or late NFW types. They're also distinct when it comes to microlensing. The NFW profiles aren't dense enough to microlens, but the power law ones lens like primordial black holes. So if you've got some of these dense 10 to the minus 11 solar mass objects, maybe we've already ruled out the post-inflation QCD Axion. If there's lots of them, then the existence of these power law profiles would be excluded by microlensing, but we don't know how many there are. And also, if you change the axial mass, you change the mass of the mini clusters, maybe the mini clusters are just too light and they're not excluded by microlensing at all. And they're in this window here. And I just want to point out some work by Edwards and Kavanagh and co. Power law versus NFW also matters for whether you can see mini clusters with radio astronomy. If they're power law, they're dense, they survive, they collide with neutron stars, you get a radio signal that you could observe with, for example, the square kilometer array. If they're NFW, they're fluffy, they don't survive, they get tidally stripped, and you can't see them with SKA. So if they're power law, we can search for them with radio astronomy and maybe with microlensing, but we won't see them in direct detection. If they're NFW, the mini clusters, they get nice and stripped, and we can find them in direct detection. The truth is probably that you have a population of both, but we just don't know, and we need to study in more depth the M-body simulations that have been done to try and tease out these different populations. So the last thing I want to tell you in 5 minutes is direct detection. Direct detection of the post-inflation axion. And I'm going to try and tell you in 5 minutes what is in a 108-page paper to appear on the archive tomorrow. So if you don't get all the details, have a look at the paper that should appear on the archive tomorrow. So how do we detect axions? The answer is via classical electromagnetism. So here's the two relevant laws, Ampere's law and Gauss's law. And axions interact with the electromagnetic field, and they modify Maxwell's equations in this way, where phi is the axion field and g is the coupling between axions and photons, which is mass dimension -1. And the source is only non-zero if the axion has non-zero gradients or temporal variations, and it acts as an effective current or effective magnetic field. If you apply a magnetic field, then you induce via the time dependence of the axion field an electric field that is parallel to that magnetic field. And the axion is oscillating, remember, at this frequency that I told you right at the beginning. The axion field is oscillating and it's like a gigahertz. If you go up to the milli eV we saw before, more like a terahertz. So the axion is an oscillating source of Maxwell's equations. The amplitude is fixed by the dark matter density. And if we know the axion and this coupling constant g, so if we know, and for the QCD axion, they're both related too. So if we know the axion mass, we know the amplitude of sources in Maxwell's equations and what frequency they're going at. So frequency is now the thing that we have to worry about. How do you detect changes to Maxwell's equations at different frequencies? You use a resonator, okay? You want to build an electromagnetic resonator for different frequencies, but you need different technology for each frequency range. So here's the recipe for how to detect axions. You get a magnet, okay? In the presence of a magnetic field, the axion source is the electric field. Magnetic fields are nice and easy to make. You get a resonator. you put it in a fridge so that you get rid of all your background noise, and then you amplify your signal. And the question is just, what's the resonator? So the classic way to do this was put forward by C.S. Akivi in 1983, and is the well-known leader in the field, the ADMX Axion dark matter haloscope. And this is how it works. It's a microwave resonator, and the resonant frequency is essentially related to the size, right? And you can change the resonant frequency a bit by moving some rods inside that cavity. But you get, you're not going to get an order of magnitude out of changing resonant frequency. So you've got your microwave cavity, the resonance when the axion is equal to the natural frequency of the cavity. And you can, if you want a nice large volume, big microwave resonator, this works in gigahertz, okay? And the power you're producing in this cavity is 10 to the minus 22 watts. That's very small, but it is detectable if it's there using, for example, Josephson parametric amplifiers. But if we move the axion up from the micro EV range, which you get in the pre-inflation scenarios, preferred mass, to this milli EV, which could be preferred in for the post-inflation axion, we're in terahertz. And terahertz is hard. Terahertz is hard for axions for the following reason. So here's the power that you get in your cavity. We know the dark matter density. That's fixed by the Milky Way rotation curve. Nothing you can do about it. G squared over m, coupling over m. For the QCD axion, this is fixed by the mass alone. Then this is what you've got to play with, the magnetic field, the quality factor of your resonator, and the effective volume. If you just make a terahertz cavity, take ADMX and move it down to millimeter, the power you would get out is 10 to the minus 29 watts. Hopelessly small. And to tune it, you would have to move these tiny little rods on the scale of a nanometer. Also hopeless. You can overcome these problems with magnetic resonance. So then the volume, you don't care what the volume is, the frequency is no longer controlled by the physical size of the object, but by the magnetic field. And instead of having to mechanically move something, you just change your magnetic field. And you can, and with NMR magnets, for example, micro Tesla. And now you have to do some material science. Antiferromagnetic resonance happens in the right terahertz frequency. And in a special type of material called a topological insulator, the antiferromagnetic resonance couples to the electric field and can be driven by the dark matter axiom. So you do this using a type of material, using beautifully, I think this is what drew me to study this, axion quasi-particles, dynamical axion field and topological magnetic insulators. I don't have time to tell you about the theory for these things, but the idea is to use the axion quasi-particle to detect axion dark matter, which I think is a beautiful synergy of this idea. So the cartoon of the experimental concept is this. Your resonator is now an antiferromagnetic topological insulator, and I call this proposal 2RAD for topological resonant axion detection. So you just replace your fridge, your microwave cavity, with a crystal of this special type of material. The way that you actually compute the power then turns into being something like a Fabry-Perot resonator. Again, I won't go into this, but happy to answer questions on it. The punchline is the forecast for the detection capability. So we think with these two different types of materials in various different experimental configurations, you might be able to detect the QCD Axion, which is this band here, in a mass range, unfortunately not the 1 milli eV that I told you it would be, the Go-Getter result, but a little bit higher, up towards the supernova 1987A bounds. Now this is just one idea among many to search for axions. As I said, the future is so exciting in this field because this is what we think the future will look like. The bounds I showed you before were the existing bounds from ADMX here. All these different open regions in this plot with names like Abracadabra and Dance and Mad Max and Organ, and you see also here 2RAD with some of our older projections, are going to come in the next decade or so and fill in this QCD Axion band and get us into the state of affairs that we're in today, where we've made really good progress against the theories. So that brings me to the end of my talk. Sorry, I've had to go quickly through some bits of it. But here's the summary. Post-inflation QCD Axion is a messy problem where you have to solve the dynamics of topological defects. But if you can do that, you should be able to predict the Axion mass. And recent work, mine and others, pushes you towards the milli-electron volt range. In this scenario, you've got messy situation after the defects decay, large density perturbations. These collapse into things called mini-clusters, and you can try and search for them. If they're dense enough, might show up in microlensing and they might show up in radio astronomy. But if they're not very dense, they can get tidally disrupted and have a nice smooth density component that you can detect with detectors on Earth. The terahertz is hard, but if you use Axion quasi-particles, they've got a nice terahertz resonant frequency, and you might be able to detect the post-inflation Axion. So there you go. That's the end of my talk, and I'm very happy to take questions and discuss.
Thanks very much, David. Let me clap for everyone, as is customary. And that was great, and you covered an enormous amount of things. Are there any quick questions before we take a short break and then have more longer discussion? Maybe Sam can ask a nice question.
Hi, very, very nice talk. Yeah, very informative, and yeah, learned a lot. One thing I would say, so I noticed that you had cited my paper was Jeremy Chang and Reuven Estig for the supernova bound, and it's a little bit higher of a mass than that. There have been kind of subsequent things by various groups that kind of have been trying to bring it down in mass a little bit, which maybe we could talk about on email. I think that they're not. So yeah, so I think that should be closer.
So you're talking about bounds that might bring this down to lower masses.
I think that should lie a little bit higher. In fact, more like 50 or 60 millieV.
Okay, yeah.
Rather than 10.
Yeah, this is something that has been reanalyzed quite a few times recently. Yeah, so I haven't had a chance to look into all of them.
There's some anyway. Yeah. So there's some things that are out there that I think are just incorrect. So I'd be happy to correspond an email about that in more detail. But I was also wondering, so there's this paper recently by Michael Dine and collaborators about the basically double counting, possibility double counting from strings and misalignment and stuff like that. And I just wondered if you had a comment on whether or not that's a concern.
I haven't read that paper. It tries to argue that you can't have that you can't have the IR dominated spectra that Gogetto and co are seeing. Yeah. So they're trying to argue you can't have the IR dominated spectra that Gogetto and co are seeing, and so you have to decide whether you trust the theoretical arguments that they're giving, which I think they don't take into account the really large gradient energies that you can have in the field, or whether you trust the numerical simulations that are really solving the nonlinear dynamics that Gogetto and co have done. I haven't read the Dine paper. I don't have a strong opinion. Yeah.
That's useful. That's useful point of view though. Thanks.